The last floating point operation we'll be discussing is division. So here I've already specified the numbers we'll be dividing, x and y. These are in decimal. Here they are converted to binary. And here they are converted to scientific notation. And then finally, here are their floating point representations. Now you should be able to confirm all of these steps on your own, but one thing you should note is that I've chosen numbers that fit perfectly into a floating point representation, so this time we don't have any nasty rounding errors. Now, in order to do this division, x divided by y, we will need to know, once again, the significands and exponents of these numbers, because we'll be computing it as x's significand divided by y's significand, and that result will be multiplied by 2 raised to x's exponent minus y's exponent. Now, the exponents are visible here in the scientific notation. So what we have is x sub s divided by y sub s times 2 raised to the power of 6 minus negative 3. So this comes out to 9. So x sub s divided by y sub s times 2 to the 9. Now in order to do this division here, we need to get the significands, and in this case it will be these bits in the floating point representation preceded by a 1 and a binary point. In other words, this value divided by this value. So let's see how you would do long division in binary. We're doing x divided by y, so we want to see how many times y significand can fit into x's significand. So I take y's significand, put it here, and then I'll be doing long division, and I take this value, x is significant, and put it under here. 1.011, 011, 01011. And I'll start off by moving the binary point over here until it reaches this barrier. Now I'll move that point over in both the numbers at the same time. So if it moves here 1, 2, 3, 4, 5 spaces, it also needs to move here 5 spaces. 1, 2, 3, 4, 5. That means our final result will have a point there. And now we can start the division. So this is a 6-digit binary number, and so we're going to need at least 6 digits here to see if this fits in. So 1, 2, 3, 4, 5, 6. And all we need to ask ourselves is whether or not the number that these first 6 digits make is greater than or smaller than this number. Now it happens to be this number happens to be larger, therefore this number can fit into it one time. 1 times that number gives us 1, 0, 0, 1, 0, 1. And then we subtract and carry on as we would with normal long division. So 1 minus 1 is 0, 0 minus 0 is 0, 1 minus 1 is 0, 1 minus 0 is 1. And then we have 0 minus 0 is 0, and 1 minus 1 is 0. So these spots are both blank. So we're left with this result. And now we'll draw down numbers from our original significand for x until we can fit this value into it again. So this value does not fit into that. I'll pull down a 1. This is 5 digits, so that's 6 digits. It still will not fit in. Let's pull down to 0. And now I have 6 digits here, but that number still won't fit in because this number is smaller than that one, because if I look at the positions, I have 1, 0, 0, and then here I have a 1, here I have a 0. Therefore, this is the bigger number. So I have to pull down yet another digit from this result. And note that whenever I do that, I'm putting a 0 up here in my answer. But now that I've pulled this 1 down, the question is, can this number fit in? Well, yes, it definitely can, because this has more digits than that. So it can fit in once, and I get a result of 1, 0, 0, 1, 0, 1. I subtract these, 0, 0, 0, 0, 0, and here 2 minus the 1 gives us a 1 there. And now I have 6 digits again. Pull down a 0. I have 7 digits. That's more digits than this number. Therefore, I can definitely fit a 1 in. So I multiply by 1, 1, 0, 0, 1, 0, 1, and subtract again. And this subtraction requires a lot of borrowing because I have nothing but zeros up here. So if I borrow 1 from a position over, then I basically have 2 this column. But that 1 had to be borrowed from over there, which had to be borrowed from here, which was from there, which was from there. So all of these become 1s. And this 1 is no longer there, it's a 0. So 2 minus 1 is 1, 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 0 is 1, and then 1 minus 1 is 0, so I'll leave that. And I'm left with 1, 1, 0, 1, 1. Pull down next 1. And can this fit into that? Yes, it can. So I get 1, 0, 0, 1, 0, 1. Subtract. 0, 1, 0, 0, 1, 0 there. Then I pull down this last one. I get a 1 there. And this number is exactly that number. So of course it fits in once. I multiply this out. I subtract, get a 0, and that means I'm done. Now, if I hadn't been done, I could have padded the right side of this with more zeros and continued as long as I needed to, either until the division ended with no remainder, or I could have kept going until I surpassed 23 digits in this result here past the binary point, since, of course, I can only store that many in my floating point representation anyway. But in this case, the division works out nice and evenly. So this is my result, and that means that this result here comes out to 1.001111, that's in base 2, of course, times 2 to the 9, which is in base 10. And now I just need to put this number into its floating point representation. So I need to bias the exponent by adding 127 to it. So 9 plus 127 equals 136. And the floating point representation will be following. So I start with a 0 because this is a positive number. 136 in binary is 1, 0, 0, 0, 0.1000. So that's the biased exponent. And then I need 23 digits here. And I'm using, remember, only these values to the right of the binary point. And once again, I need this result to be in normalized form. I got lucky in that it came out in normalized form automatically. But if this point had not been immediately to the right of the leftmost one, I would have had to mess with the exponent to make that work out. But as it is, I got lucky, so I have 0, 0, and 4 ones, 1, 2, 3, 4. And then I need enough zeros to fill this out. So 1, 2, 3, 4, 5, 6. And then I'll fill this out. So enough zeros that I have 23 bits here and no rounding needed at the end. So I get a nice clean result here that is equal to 632 in base 10. And if you divide these numbers directly in a programming language, you should find out that you get that exact answer precisely. So no rounding error this time.